அது சொல்லிட்டு இது சொல்லுங்களா பேசலாங்களா? Hi students, welcome to Future Doctor NEET Academy for the crash course in NEET Physics. This is a crash course in NEET Physics for the live stream NEET Physics. And chapter, that is topic today we are going to discuss is from chapter 13, Kinetic Theory of Gases, chapter 14, Oscillations, chapter 15, Waves. Okay, chapter 13, Kinetic Theory of Gases, or simply Kinetic Theory. Kinetic Theory of Gases. To study kinetic theory of gases, we want to learn some of the laws, basic gaseous laws. That is Boyle's law, Charles' law, Gay-Lussac's law. First, we will discuss Boyle's law. Boyle's law states that at constant temperature, volume of given mass of gas is inversely proportional to its pressure. This is Boyle's law of gases. State Boyle's law, at constant temperature, volume of given mass of gas is inversely proportional to pressure. V is inversely proportional to pressure, or by removing proportionality, we will have constant, that is V is equal to constant by pressure, or pressure into V equal to constant. P into V, pressure into volume is constant. This is Boyle's law. This is applicable only when temperature maintained constant. At constant temperature, when pressure increases, volume decreases. Volume increases, pressure decreases. Second law is Charles' law. Charles' law states that at constant pressure, volume of a given mass of gas is directly proportional to its absolute temperature. What is absolute temperature? Because last class only we discussed. What is the meaning for absolute temperature? Or simply say, what is absolute temperature? Last class only we have discussed. Temperature is measured in many scales. What is the scale? Different units of temperature. Come on, unit of temperature. Celsius, Kelvin, Fahrenheit. And absolute temperature means temperature measured in Kelvin. That is only absolute temperature. Okay. Temperature may be in degrees Celsius or Fahrenheit, but you must convert to Kelvin. Okay, that is SI unit. That is absolute temperature. Then, at constant pressure, volume of a given mass of gas is directly proportional to absolute temperature. V is proportional to T, or V by T equal to constant. This is Charles' law. And Gay-Lussac's law, it states that at constant volume, pressure of a given mass of gas is directly proportional to its absolute temperature. At constant volume, pressure of a given mass of gas is directly proportional to its absolute temperature. P by T is constant. P is proportional to T and P by T is constant. So, this is the various laws of gases based on kinetic theory of gases. ideal gas equation. For n mole of gas, n is the number of mole of gas, PV equal to N or T. This PV equal to RT or nRT is a combination of all the three laws of gases. Okay, that is ideal gas equation, PV equal to N or T. For 1 mole, N equal to 1. N is the number of moles. For n mole, N equal to 1. If you substitute, PV equal to RT. And you know, P is a pressure, V is a volume, and T is a absolute temperature. And R is a constant called universal gas constant. R is a constant called universal gas constant. Its value 8.31 joule per mole per Kelvin, or 8.31 joule mole power minus 1 Kelvin power minus 1. And there is a relation between R, universal gas constant, Boltzmann constant K, and Avogadro number. That is, Kb is a Boltzmann constant equal to R by Na. Kb is a Boltzmann constant, R is a universal gas constant, Na is the Avogadro number. And Kb is a Boltzmann constant. What is the value of Boltzmann constant? Kb equal to 1.38 into 10 power minus 23. Joule per Kelvin. And what is the value of Avogadro number? Yes, 6.023 into 23. 10 power 23 or 26? 10 power 26. In physics, 10 power 26. In chemistry, we may use 10 power 23, I think. Is it so? In physics, 10 power 26. In problem, we will explain about this. Okay. So, this is the Avogadro number. And ideal gas equation. This is only ideal gas equation, PV equal to nRT. And what is ideal gas? A gas which obeys gas law strictly is an ideal gas or perfect gas. A gas which obeys gaseous law are called ideal gas or perfect gas. And the molecules of such a gas are of point size and there is no force of attraction between them. This is the assumption we are keeping. The molecules of such a gas are of point size and there is no force of attraction between them. Assumptions of kinetic theory of gases. All gases consist of molecules which are rigid. What is rigid? Rigid body is a body. By application of force, there is no relative displacement between the particle. That is a rigid body. And elastic spheres identical in all respect for a given gas. And second point, the size of a molecule is negligible as compared with the average distance between two molecules. Size of molecule is negligible as compared with the average distance between the two molecules. It means size of the molecule is very small compared with the distance. Its meaning is that gaseous molecules are somewhat far distance apart. And during the random motion, actually molecules of the gases are moving randomly in all the direction. That is another important assumption. And during the random motion, the molecules collide with one another and with the wall of the vessel. During the random motion, the molecules collide with one another and with the wall of the vessel. And the collisions are almost instantaneous. What is instantaneous meaning? Yes? immediately, that is a no delay. Collision will take place instantaneously, continuously. Okay, in a given interval of time, continuously. And the molecular density remains uniform throughout the gas. The density of the molecule is constant. The collisions are perfectly elastic in nature, and there are no forces of attraction or repulsion between them. Elastic collisions are elastic collision. What are elastic collision? We studied in previous topic. What are elastic collision? Even before and after collision, there is no change in the kinetic energy or velocity or speed of the molecule. That is elastic collision. Okay, that is kinetic energy is constant, and there are no forces of attraction or repulsion between them. That is, force will be there, the force will be negligible compared with the collision. Pressure exerted by gas. These are all for problem purpose we may use. Pressure exerted by gas P equal to 1 by 3 m by v into v bar square. Capital V is the volume and capital M is the mass of the gas, and mass per unit volume is density. Density of a gas. We know density equal to mass by volume. Density equal to mass by volume. So, m by v is replaced by rho. 1 by 3 into rho into v square. Here v bar square is the mean square of the mean square value, mean square of the velocity or speed. And 1 by 3 into, we can write this rho as m into n v square. What is m? M is a mass of each molecule, and n is the number of molecules per unit volume. Okay, n is the number of molecules per unit volume. So, rho can be replaced as m into n. Rho equal to m into n. M is the mass of each molecule and n is the number of molecules per unit volume. That only we will say as a molecular density. N will be a molecular density. Noted, no? Average kinetic energy of a gas. If m is a molecular mass and v is the molecular volume and small m is the mass of each molecule, then mean kinetic energy per mole of a gas equal to half m v square. And this is equal to 3 by 2 RT or 3 by 2 KNT or equal to PV. That is work done equal to pressure into volume. So, that is equal to energy, 3 by 2 of energy, 3 by 2 of PV. P is a pressure, V is a volume. So, kinetic energy of mv square equal to 3 by 2 PV. P is a pressure, V is a volume. Also equal to 3 by 2 RT. R is a, what is R? Gas constant. T, absolute temperature, equal to 3 by 2, that is R equal to K into N or KB into Na. K is a Boltzmann constant, Na Avogadro number. Okay. And mean kinetic energy per molecule of a gas E equal to half m v bar square is the average velocity or mean velocity, mean square of the velocity equal to half into kBt. Kb is a Boltzmann constant, and kinetic energy of 1 gram of gas equal to half mv square equal to 3 by 2 or T by m naught. M naught is the gram molecular weight. M naught is called gram molecular weight. Noted? Avogadro law. Avogadro law states that equal volume of all gases under similar condition of temperature and pressure contain equal number of molecules. This is the Avogadro law. Equal volume of all gases under similar condition of temperature and pressure contain equal number of molecules. That is Avogadro number equal to 6.0225 into 10 power 23 per mole. I said no in physics 10 power 26. That is, if it is expressing in gram, 10 power 23. In kilogram, mostly we will follow in SI unit only in physics. So, if it is expressing in kilogram, 10 power 26. In that way only I said Avogadro number is 6.0025 into 10 power 26. Okay. And here we mentioned as previous number gram molecular weight in terms of gram, so into 10 power 23. And next is Graham's law of diffusion. Graham's law of diffusion states that rate of diffusion R is inversely proportional to square root of the density. This is the Graham's law of diffusion. State Graham's law of diffusion. Rate of diffusion R is inversely proportional to square root of the density. Okay. Then it means, suppose if you have two different gases having two different density, then there will be a two different rate of diffusion. That is R1 rho 1. Another one R2 is inversely proportional to 1 by square root of rho 2. Then R1 by R2 means proportionality will be removed, equal to square root of rho 2 by rho 1. That is only this formula. Okay. So R1 by R2 equal to square root of rho 2 by rho 1. This is the rate of diffusion, ratio of the rate of diffusion of two gases based on Graham's law. State Graham's law of diffusion. Rate of diffusion is inversely proportional to square root of the density. Okay, noted. Dalton's law of partial pressure. Total pressure exerted by a mixture of non-reacting gases occupying a given volume is equal to the sum of partial pressure which gas would exert if it alone occupied the same volume at a given temperature. This is Dalton's law of partial pressure. Total pressure exerted by a mixture of non-reacting gases occupying a given volume is equal to the sum of partial pressures which gas would exert if it alone occupied the same volume at given temperature. P equal to P1 plus P2 plus P3. This is only sum of partial pressures of a gases. So total pressure exerted is equal to P1 plus P2 plus P3 plus like that. Next topic is average speed. Average speed, root mean square speed, probable speed, like the different speeds are there. Average speed, V bar equal to, or V average equal to V1 plus V2 plus V3 plus up to Vn. If it contain n number of molecule, then V1, V2, V3 up to Vn is the velocity of the each molecule divided by n number of molecules. This is the average speed. Okay. Average speed equal to V1 plus V2 plus V3 up to Vn divided by n. And in terms of temperature and m, V bar equal to square root of 8 kBT by pi m. M is the mass of the molecule. M naught is the molecular mass. V bar equal to 8 kBT by pi m. K is the Boltzmann constant. And in terms of R value, gas constant R value equal to square root of 8 RT by pi m naught. There is a relation between K, N, or by simplifying we will get this one. So average speed can be expressed in two forms. One is in terms of kb means square root of 8 kbt by pi m, and in terms of r means square root of 8 rt by pi m naught. Okay. Next, root means square. Root means square velocity or root means square speed. This is equal to square root of v1 square plus v2 square up to vn square divided by n. Average means mean square, root mean square means square root of this one. VRM equal to square root of v1 square plus v2 square up to vn square divided by n. And in terms of k, t or rt means VRMS equal to square root of 3 kbt by m or square root of 3 rt by m. And already we may know RT equal to PV, then substitute 3 PV by m. That is, energy or work is equal to pressure into volume, P into V. So RT can be replaced as PV. Therefore, square root of 3 kT by m or square root of 3 RT by m equal to square root of 3 PV by m. Same way here also we can write square root of 8 PV by pi m naught also. Okay. Then most probable speed, VMP or simply VP. V probable speed or most probable speed equal to square root of 2 kbt by m or square root of 2 RT by m. 2 kbt by m or 2 RT by m or 2 PV by m. Relation between average speed, VRMS, root mean square speed, and VMP, most probable speed. V bar equal to 0.92 times of VRMS and V most probable equal to 0.816 times of VRMS. And if you write the ratio between these three, VRMS is to V average is to V most probable equal to 1.73 is to 1.6 is to 1.41. Okay. VRMS is to V bar is to VMP equal to V, that is 1.73 is to 1.6 into 1.41. That is, the other things are getting cancelled. KT by M or whatever will be getting cancelled, and that root 2, root 3, root 8 by pi, that only will be existing. On simplifying, we are getting these things. Okay. Noted? Noted, no? Degrees of freedom. Degrees of freedom F equal to 3n minus k. What is degrees of freedom? Degrees of freedom is the number of atoms or whatever having, which is used to specify the motion. Suppose that is in single dimension means only one, that is a x-axis, y-axis, z-axis, 3 degrees of freedom, like that we will discuss in problems. So F equal to 3n minus k, and here n is the number of atoms in a molecule and F is the number of degrees of freedom. That is the number of individual coordinate required to specify the motion, that is the degrees of freedom. Okay. And k equal to number of, for example, they will say ant. For example, ant is moving on a floor, only on a floor. Then it has 3 degrees of freedom, x-axis, y-axis, and here 2 only. Suppose it can crawl in other way means, then we may say as a z also. At present, it is 2 degrees of freedom. And if it can move in all the 3 dimensions, it has 3 degrees of freedom. Okay. That's the number of individual coordinate required to specify the motion. That is the degrees of freedom. And for monoatomic gas, 2 degrees of freedom. For diatomic gas, 5 degrees of freedom. Just one example given. And law of equipartition of energy. For any thermodynamical system in thermal equilibrium, the energy of the system is equally divided among its various degrees of freedom, and energy associated with each degree of freedom corresponding to each molecule is of kT. Okay, this is equal to of kT. Here K is the Boltzmann constant and T is the absolute temperature. So from law of equipartition of energy, that is energy is equal to of kT. In terms of degrees of freedom we will do. And law of equipartition of energy holds good for all degrees of freedom, whether translation, rotational or vibration. I said 3 degrees of freedom is only for translation. Okay, translation is 3 degrees of freedom as x-axis, y-axis, z-axis. Suppose rotational only 2, then 3 plus 2, vibrational 2 or 3 plus 2, like that we will do. And a monoatomic gas molecule has only translational kinetic energy as 1 by 2 mvx square, that is along x-axis, speed along x-axis, of mvy square along y-axis, and plus of mvz square along z-axis. So here 3 degrees of freedom, we can say n by 2 kT, n equal to 3, so 3 by 2 kT. That's not mentioned here. Okay. That is, so formula here is degrees of freedom E equal to, in terms of degrees of freedom, n by 2 kT. N is the number of degrees of freedom. N or F will be used for degrees of freedom. Okay. So for monoatomic gas, only translation kinetic energy, only translation motion possible means it has 3 degrees of freedom, n equal to 3. Then E equal to 3 by 2 kT, that only this. Okay, E equal to 3 by 2 kT. So monoatomic gas has only 3 degrees of freedom, and in addition to translation kinetic energy, a diatomic molecule has 2 rotational kinetic energy, 2 rotational motion. So E translation plus E rotation. E translation is along x-axis, y-axis, z-axis, this 3. And rotational motion along y-axis, z-axis, this 2. So 3 plus 2, how much? 5. So degrees of freedom for this is monoatomic, and for diatomic, E diatomic is equal to, that is 5 by 2 kT. Okay, this is for kinetic energy for diatomic molecule in terms of degrees of freedom, that is 5 by 2 kT. Okay, noted? At very high temperature, vibration is also activated, due to which 2 extra degrees of freedom emerge from vibration energy. So translation motion 3, rotational motion mentioned 2. Apart from that, high temperature vibration also takes place. During vibration, 2 more extra degrees of freedom. Hence, at very high temperature, that is 3 plus 2 plus 2. 3 is for translation, plus 2 is for rotation, and another 2 is for vibration. So 7 degrees of freedom. Each translation, rotational degrees of freedom correspond to 1 mole of absorption of energy, and as energy 1 by 2 kT. Internal energy and specific heats of monoatomic, diatomic and polyatomic gases. If F or N will be used as a degrees of freedom, then for a gas of polyatomic molecules, energy associated with 1 mole of gas, U equal to F by 2 RT. U equal to F by 2 RT, and CV equal to F by 2 R. CV equal to F by 2 R. What is CV? CV is the specific heat capacity at constant volume, and CP is the specific heat capacity at constant pressure. CV is the specific heat capacity at constant pressure, sorry, volume, at constant volume. And Cp is the specific heat capacity at constant volume. Sorry, pressure. Specific heat capacity at constant pressure, that is Cp at pressure. And U equal to F by 2 RT, and actually U equal to Cv by Ct. U equal to d by dt of Cv. Then T getting cancelled, F by 2 R. And Cp equal to 1 plus Cv, that is the relationship between this. Next chapter we will discuss. So Cp equal to 1 plus Cv, that is a formula. On substituting, Cp equal to 1 plus F by 2 R, that is 1 plus 2 by F. And here gamma is nothing but, what is gamma? Gamma is the ratio between the specific capacity at constant pressure and constant volume, equal to 1 by 2 plus 1 plus 2 by F. 1 plus 2 by F. Gamma is the ratio between specific capacity at constant pressure and constant volume. Okay. Noted? For monoatomic gas, F equal to 3 degrees of freedom. That is only translation motion. So, U equal to 3 by 2 RT. That is 3 is degrees of freedom. F for N will be used. 3 by 2 RT. And Cv equal to T will be removed. As we said, U equal to d by dt of Cv. So, that will be removed. Oh, sorry, your capital T. 1 minute. This is capital T. D by dt of Cv, then only T will getting cancelled. Yes. Then U equal to 3 by 2 RT or Cv equal to 3 by 2 R, dt getting cancelled. Then Cp equal to 1 plus 3 by 2 R. Cp equal to 1 plus 3 by 2 R. So 2 plus 3, 5 by 2, that only this. Cp equal to 5 by 2 R. Then gamma equal to Cp by Cv, I said. Gamma equal to Cp by Cv. That is, gamma equal to Cp is 5 by 2 R. 5 by 2 R divided by Cv is 3 by 2 R. 3 by 2 R getting cancelled, 2 getting cancelled. 5 by 3. 5 by 3 is 1.66. That only this. Okay. Similarly, for diatomic gas with no vibrational mode, only 2 only. That is 3 is for translation mode plus 2 is for rotational mode. 3 is for translation mode and this is for rotational mode. Then 5. Then U equal to 5 by 2 RT. U equal to 5 by 2 RT and Cv equal to 5 by 2 R. Cp equal to 1 plus 5 by 2 R, that is 7 by 2 R. Okay. 1 plus 5 by 2 R, that is 7 by 2 R equal to gamma, and gamma equal to 1.4. That is 7 by 5. Cp by Cv, 2 R getting cancelled. 7 divided by 5, you will get 1.4. Gamma is 1.4 for diatomic gas. Even for air, value of gamma is 1.4. Okay. For a diatomic gas with vibrational mode, that is at high temperature. This is possible at high temperature. At high temperature. Then F equal to 7. That is 3 plus 2 plus 1. 3 is for translation, 2 is for rotational, and next 2 is for vibration. Then U equal to 7 by 2 or T. U equal to 7 by 2 or T, and CV equal to 7 by 2 R. And CP equal to, come on, can you say what is CP? CP equal to 1 plus 7 by 2 R. CP equal to 1 plus 7 by 2 or how much? 9 by 2 R. That is CP. And what about gamma? Gamma equal to 9 by 7 will come. Is it so? Is it so? 9 by 7 how much? 717. And then 20, 7 to 14, 6. Gamma equal to CP by CV, no? Gamma equal to CP by CV, and CP is 9 by 2R and CV is 7 by 2R. Okay. Just for example, I put one, and other thing all directly I said. Okay. So here R2 getting cancelled, so 9 by 7. Now 9 divided by 7. Okay. Understand? And this how much is coming? 717, 20, 7 to 14, 6. .28, no? Is it? 1.3 something. 20 means 7, approximately you are saying. Okay. So 1.28 something as approximately means 1.3. Okay. Then this is a table for degrees of freedom, average kinetic energy and internal energy for monoatomic, diatomic and polyatomic gas. 3 degrees of freedom, diatomic 5, and for polyatomic or triatomic will be say 6. And for average kinetic energy per molecule, 3 by 2 kT, 5 by 2 kT, 6 by 2 kT as 3 kT. Internal energy U, 3 by 2 RT, 5 by 2 RT, 6 by 2 RT as 3 RT. Mean free path. Mean free path is the average distance covered by a molecule between 2 successive collisions. That is called mean free path. Average distance covered by a molecule between any 2 successive collisions. As we said, according to kinetic theory of gases, molecules are moving randomly in all the direction. So during that it undergoes elastic collision. That and all we discussed in kinetic theory of gases. Okay. So it is the average distance between 2 molecules covered by a molecule between 2 successive collisions. Here it collides with one molecule, and after some time, after some distance, may collide with the another molecule. So there will be a distance will be taken as an average. That average only, average distance covered by a molecule between any 2 successive collisions. Successive collision means next to next collision. That is mean free path, denoted by a symbol lambda. And lambda equal to 1 by root 2 into n pi d square. Here n is the number density and d is the diameter of the molecule. Okay. In this many times, not only problems, in this directly formula will be asked many times. That is, a lambda is proportional to, that is the average distance lambda is proportional to d square, or inversely proportional to d square, or proportional to d square, like that. Different formula like that. Many times this, in this way questions will be asked. Okay. That is, lambda is proportional to 1 by d square or inversely proportional to d square is the correct answer. Here n is the number density. Next, Brownian equation. Brownian equation is a zigzag motion of gas molecule is Brownian motion which occurs due to random collision of molecules. Random collision of molecules. Noted? Okay. Next is chapter 14, oscillations. What is an oscillation? Simply, what is the definition for oscillation? To and fro motion or back and forth motion, that is called oscillation. What is the name of this simple pendulum? Question also very simple. What is oscillation? To and fro motion. This is to and this is fro. To and fro motion, that is oscillation. Okay. To and fro motion or back and forth motion, that is called oscillation. A motion which repeats itself over and over again after a regular interval of time is called periodic motion. A motion which repeats itself over and over again after a regular interval of time is called periodic motion. Oscillatory or vibratory motion is that motion in which body moves to and fro or back and forth repeatedly about a fixed point in a definite interval of time. That is called oscillatory motion or vibratory motion. That is, all the oscillatory motion are periodic motion and all the periodic motion are not oscillation. For example, Earth revolves around the Sun in an elliptical orbit that we studied in gravitation. Okay. Is it a oscillatory motion? Yes. So, but that is a periodic motion. Is it so? Earth revolves around the Sun after 1 year. It repeats itself in a regular interval of time. What is the interval of time? 1 year or 365 1/4 days. That only we are saying 1 year, 1 annual period. Okay. So, that is a periodic motion, repeat itself over and again in a given interval of time, but it's not in oscillatory motion. It's going round. Okay. That's why these two are different. Oscillatory motions are periodic, but all the periodic is not oscillatory motion. For oscillatory motion, best example, simple pendulum only. Okay. Another example, that is in string instrument, when we are plugging this, what will happen? It starts to vibrate like this. So, this also this is a vibratory motion or oscillatory motion. Okay. It starts to vibrate up and down in string instrument, veena, violin, there and all. So, that is a vibratory motion that comes under oscillatory motion. And simple harmonic motion is a specific type of oscillatory motion in which particle moves in one dimension. Particle moves in one dimension, one axis only, x axis, y axis, like that. And particles moves to and fro about a fixed mean position. Here net force equal to 0. And net force on the particle is always directed towards mean position. And magnitude of net force is always proportional to the displacement of particle from the mean position at that instant. And F net equal to minus kx, that is F is proportional to x, and minus negative sign indicates that force is acting always opposite to the direction of displacement, that is negative sign. And by removing proportionality, we are having constant, that constant only k into x. Okay. And here k is a constant called force constant. So, F equal to minus kx and k is a constant called force constant. Force constant. Its unit is Newton per meter. That is the unit of force constant. See, K is a force constant, and from Newton's second law, F equal to ma. F equal to ma, therefore ma equal to minus kx, or a equal to minus k by m of x, and k by m equal to omega square, that is a equal to minus omega square x. That is here omega square equal to k by m, and your omega is the angular frequency. Omega is called angular frequency, and from this only we will do many problems as omega equal to square root of k by m. Then we know a is the acceleration is nothing but rate of change of velocity, and velocity is nothing but rate of change of displacement. If you substitute this here, a equal to d by dt of dx by dt. This is only given as a equal to d square x by dt square. That only this one. So acceleration a equal to d square x by dt square. That is nothing but differentiate x with respect to t twice, 2 times. So d square x by dt square equal to minus omega square x, and this equation is called differential equation of simple harmonic motion. This equation is called differential equation of simple harmonic motion, and the general expression for x of t satisfying the equation is x of t equal to a sin omega t plus phi. A sin omega t plus phi. Here a is called amplitude, and omega is the angular frequency, t time, phi phase, initial phase phi. Okay. So x of t equal to a sin omega t plus phi. So this gives the equation of wave. Suppose there is a wave moving in x axis like this. Like this along x axis, and a is the displacement. Then this is the formula, that is displacement of a particle at t time is equal to a sin omega t plus phi. Okay. Some important terms we want to learn for oscillatory motion. Same thing apply for waves also, next chapter. Here we will say oscillation, there wave. Amplitude. What is amplitude? Amplitude of a particle executing simple harmonic motion is its maximum displacement on either side of the mean position. This is a wave means, then maximum displacement of the particle either side of the mean position. This is the mean position. Okay, this is the mean position, and this is amplitude. What is amplitude? Maximum displacement of the oscillating particle from its mean position, both the side from the mean position. That is amplitude, denoted by a symbol A. Okay, and time period. Time period of a particle executing simple harmonic motion is the time taken to complete one cycle. Time taken to complete one cycle. Suppose this will be one cycle. Complete one wave is a one cycle from year to year. Okay. So we can say this is complete time period for one cycle. Then time period t equal to 2 pi by omega. And already we said omega equal to root of k by m. I said no in previous, see, omega equal to root of k by m. That we are substituting here. T equal to 2 pi by omega and 2 pi into root of m by k. So T equal to 2 pi into root of m by k, that is the time period, unit of time period second. What is the unit of amplitude? Unit of amplitude? Amplitude is a displacement. What is the unit of displacement? Meter. Okay. So time period is the time taken to one complete cycle of oscillation. In wave, time taken to complete one vibration of the wave, one complete wave. Okay. Next, frequency. Number of oscillations completed in 1 second. That is called frequency. What is frequency? Is a number of oscillations executing simple harmonic motion in 1 second. That is called frequency. And its formula is nu equal to, is the frequency nu equal to omega by 2 pi, that is equal to 1 by 2 pi into root of k by m. 1 by 2 pi into root of k by m. Next, phase. And what is the unit of frequency? Unit of frequency. Frequency is a reciprocal of time period. So what is the unit of frequency? Unit of time period? Second. So second power minus 1 we can say, but SI unit is, what is this? Hertz. Okay. Unit of frequency is hertz. Next topic, next term, phase. Phase of particle executing simple harmonic motion at any instant is as regard to its position and direction of motion at that instant. So phase represents position of a particle and also direction of motion of particle at the instant. That is only phase. And it is measured as argument, that is angle of sine in the equation of simple harmonic motion. And phase equal to omega t plus phi. That is sine omega t plus phi we will use. That only argument value. Sine omega t plus phi. At t equal to 0, at t equal to 0, phase equal to phi. So that this phi we are calling initial phase. Phi is called initial phase. And t is 0 means phi is the initial phase of the particle or phase constant. Okay. So what is phase? Phase is a state which regards the position and direction of motion at that instant, at a given instant. We said no, that is in LCR circuit and all, current leads the voltage by pi by 2 or voltage leads the current by pi by 2. So that indicates the position and direction of motion at given instant of time. And some important relations. Position. This is a wave. Okay. And this is a plus A. Maximum amplitude is a plus A and minus A. And I said no, time period is for one complete wave. Time taken for one complete wave is time period. So one complete wave, this is 1t. Half of that t by 2. And maximum displacement along positive direction is plus A. Along negative direction is minus A. And small a represent what is A? A is the amplitude. And if mean position is at origin, the position depends on time in general as x of t equal to sine omega t plus phi. And at mean position, at x equal to 0, it is 0. And at x equal to maximum value, it will be maximum. So At here it's 0 and maximum it goes like this. And we know for sine formula, for sine, theta equal to 0, then sine 0 is 0. And theta equal to 90, sine 90 is 1. So 0, 1, 0, 1 like that. So it follows a sine wave. Okay, it follows a sine wave. We can say this is a sine wave. At mean position, x equal to 0. At extreme position, this is plus a or minus a. Plus a, capital A or use or small a, whatever. Plus a or minus a. Okay. And velocity. At any instant, velocity v equal to a omega cos omega t plus phi. That is, we know formula for v and dx, v equal to dx by dt. And x equal to, what's the formula? A sin omega t plus phi. Is it? Then dx by dt, that is only v. V equal to dx by dt. If you differentiate this, a into cos omega t plus phi, sin omega t, sin theta, if you differentiate, cos theta, into omega, that only a omega cos omega t plus phi. This is equal to v. Okay. Then, at any position, v of x equal to omega into square root of a square minus x square, plus or minus omega square root of a square minus x square, and velocity is minimum at the extreme position. At the extreme position, it is minimum because the particle is at rest. That is, v equal to 0 at the extreme position. See, at extreme position, v equal to 0, and velocity is maximum magnitude at mean position. See, at mean position is here. At 0, how is the velocity? Maximum. Okay, at 0 it is maximum. Therefore, it follows what type of wave means this is the cosine wave. Cos wave or cosine wave. Then, velocity has maximum magnitude at mean position, that is v max equal to omega into a at mean position. V max equal to omega into a at mean position. Noted? Acceleration. Acceleration is rate of change of velocity. So velocity we derive now, that is a omega cos omega t plus phi. That again we want to differentiate and simplify. Then we will get at any instant t, this is equal to omega square a sin omega t plus phi. At any position x, a of x equal to minus omega square x. And acceleration is always directed towards the mean position. And at mean position, a minimum equal to 0, and at extreme position, it is omega square a, maximum value. Okay. So this is the formula for this, and this also follows sine wave. Energy. Kinetic energy. Kinetic energy K equal to of mv square. Of mv square equal to v, we know v equal to omega square a square minus x square we know. So on substituting, of into m omega square a square minus x square. Okay. And also we know in another term as m omega square a square cos square omega t plus phi. Then this is the waveform for kinetic energy. That is, for one t it will goes like this, t by 2 and t. And K is maximum at mean position, minimum at extreme position. And K max equal to of m omega square a square and of k a square at mean position. And K minimum equal to 0 at extreme position. Okay. So K max equal to maximum kinetic energy. This is for any time. For any time of m omega square a square cos square omega t plus phi, and for maximum K max equal to of m omega square a square. Potential energy. If potential energy is taken as 0 at mean position, then at any position u of x equal to of into k x square equal to of into m a square omega square sin square omega t plus phi. And u is maximum at extreme position as of k a square, and u is minimum at mean position. So this is the wave for potential energy. Next to total energy. Total energy is equal to of k a square or of m a square omega square, and wave for total energy is straight. And this is the energy position graph for all the three energy: kinetic energy, potential energy and total energy. Kinetic energy like this, potential energy like this, and adding these two only total energy. So at any time, at any point, any time, total energy is constant, is going as constant. That only here. See, at particular time, at this time, how is that? At this time, kinetic energy is there, potential energy is here, but total energy here only. At any point, total energy is constant. Okay. Time period of simple harmonic motion. To find whether a motion is simple harmonic motion or not, and to find its time period, follow this step. That is how to do like that. And here t equal to 2 pi into root of m by k. That is a t equal to 2 pi by omega, that already we studied. That is equal to 2 pi into root of m by k. Oscillation of block connected spring. These are all problems we will do. And spring, if it is connected like this, which is kept on the frictionless table, smooth horizontal frictionless table, and K is the force constant of a spring. K is the force constant of a spring. Then, by applying a force, it will start to oscillate or vibrate like this. Then, its time period is t equal to 2 pi into root of m by k. 2 pi into root of m by k. This is for oscillation of a spring which is in horizontal direction. Next is, note down this formula, t equal to 2 pi into root of m by k. This is for time period for horizontal spring. K is the force constant of a spring. K is a force constant of a spring. Noted? For vertical spring, T equal to 2 pi into root of m by k. T equal to 2 pi into root of m by k. This is vertical. That is, spring is connected in vertical and connected with a block. Previous is in horizontal. Spring is connected in horizontal and force is applied. Then displacement takes place in this direction. Similarly, force is applied here as elongation d plus x. It goes like this. Then time period t equal to 2 pi into root of m by k. Any difference between these two? No change. So same formula only for both vertical spring as well as horizontal spring. Then combination of springs. Suppose two springs are connected in series. two springs connected in series like this, K1, K2. Then just like resistor, two resistor connected in series, two capacitor connected in series, two inductor connected in series. The effective resistance, effective capacitance, effective inductance we study, no? Same like that, here is effective force constant. K equal to formula 1 by K equal to 1 by K1 plus 1 by K2, or K equal to K1 into K2 by K1 plus K2. Here K1, K2 are the spring constant of each spring. Okay. Noted? Noted? When two springs are connected parallel like this, then K equal to K1 plus K2. K equal to K1 plus K2, just addition. The effective spring constant is the just adding these two. When it is connected series only, reciprocal. And suppose two springs are connected like this. Is it series or parallel? Parallel. Good. It's just like this. It's a parallel. Okay. So for this also K1 plus K2. Okay. Oscillation of a cylinder floating in a liquid. That is, for that T equal to 2 pi into root of L by G. Note down this formula. T equal to 2 pi into square root of L d by rho G, that is equal to 2 pi into root of L by G. Time period T equal to root of L by G. L is the distance immersed in the liquid. Cylinder which is immersed in the liquid. Capital L will be a total length of the cylinder. Okay. And liquid oscillating in a U tube. T equal to 2 pi into square root of m by 2a rho g equal to 2 pi into L by 2g. Here L is the length of the liquid column. L is the length of the liquid column. T equal to 2 pi into root of L by 2g. Noted? Noted? Angular oscillations. So far we discussed this linear oscillation, like that angular oscillation also takes place. Instead of straight line motion, if a particle or center of mass of a body is oscillating on a small arc of a circular path, then it is called angular oscillation or angular simple harmonic motion. For angular simple harmonic motion, tau is proportional to theta, or tau equal to minus k into theta. In there we used force F equal to minus k into x. Here tau equal to minus k into theta, and here also k is a force constant only, and I alpha equal to k theta. Therefore time period t equal to 2 pi into square root of I by k. Time period t equal to 2 pi into square root of I by k. I is the moment of inertia. There m we used as mass, here moment of inertia I. Noted? Simple pendulum. For simple pendulum, T equal to 2 pi into root of L by G. T equal to 2 pi into root of L by G. L is the length of the pendulum, G is the acceleration due to gravity. And time period of a pendulum when it is in a lift. In this some problem we may discuss. Time period of a pendulum when it is in a lift, so that is if lift is acceleration of a lift is upward, that is lift is moving upward, then T equal to 2 pi into square root of L by G plus A. G is the acceleration due to gravity on earth, 9.8 meter per second square. A is the acceleration of a lift, and T equal to 2 pi into square root of L by G minus A if acceleration of lift is downwards, if it is coming down. Lift is moving upward, G plus A, moving downward, G minus A. And seconds pendulum, time period of seconds pendulum is 2 seconds. And length of seconds pendulum on earth is 1 meter. Length of second pendulum on earth is exactly 1 meter. Second pendulum is a pendulum having length of the pendulum is exactly equal to 1 meter length. For 1 meter length, time period will be 2 seconds. That is only seconds pendulum. Next, damped and forced oscillation. Damped oscillation. The oscillation of a body whose amplitude goes on decreasing with time is defined as damped oscillation. See, how is the amplitude? Amplitude is decreasing with respect to time. That is damped oscillation. Example, swing, unjal. When we swing, after some time what will happen? It comes to rest. It will not go on oscillating continuously. Why? Because of the, why the swing is come to rest? Even the pendulum also. Even pendulum also, that bob, when you oscillate, it will oscillate for some time. After some time, it will come back to rest. Why? What is the reason? Come on. Why the pendulum after oscillation come to rest? Why the swing, that is unjal, after some time oscillation, it comes to rest? Because of resistance motion of air. And also that is the elastic or resistance motion by the spring, the chain, like that. Okay. Then in this oscillation, the amplitude of oscillation decreases exponentially due to damping forces like frictional force, viscous force, etc. Frictional force only I said, that is frictional forces between the chain for swing. That iron chain, no? That one. And due to decrease in amplitude, the energy of oscillator also goes on decreasing exponentially. Exponentially means it will not come back to rest immediately, it takes an infinite time. Forced oscillation. The oscillation in which a body oscillates under the influence of an external periodic force are known as forced oscillation. That is, the swing should continue to oscillate, or the pendulum should continue to oscillate. Then what should we do? We have to give the force continuously. That only forced oscillation. Oscillation in which a body oscillates under the influence of an external periodic force are known as forced oscillation. Resonance. When the frequency of external force is equal to the natural frequency of the oscillator, then this state is known as resonance state. Okay, when the frequency of the external force and frequency of the oscillator are equal, that is called resonant force. During resonance, it will start to oscillate with maximum amplitude. Okay, maximum amplitude, it will start to oscillate. And this frequency is known as resonant frequency. Okay. Okay. Last chapter, 15th chapter, waves. Waves or wave motion. Waves or wave motion. What is a wave? Wave is a vibration or disturbance in space. That is a wave. I am giving speech and this is a wave, sound wave. So it produces some disturbance in the air and reaches your ear. Wave is a vibration or disturbance in space. E1CA, what is this? Water. In water, if you drop any stone, what will happen? It forms a ripples. So this ripples is a wave. Okay, this is a wave. So wave is a vibration or disturbance in a space. Here, disturbance in the water. Wave transfer energy without transferring matter. Actually, that matter is not transferring, just it transfer energy only. For example, I am giving a speech, it transfer only sound energy. It's not transferring air molecule. Okay, air molecule is not transferring. During vibration, these air molecule transfer energy from one place to other place. And how are waves classified? What material do waves move through? That is, the substance that waves travel through and need to have in order to move. That only we are calling medium. For example, for sound waves, is medium is necessary or not necessary? Medium is not necessary. Suppose air is not present here. Is my speech will hear by you, audible to you? If no air is there, vacuum is there, then my voice, is it audible to you or not audible to you? So, medium is necessary. Okay. For sound wave, medium is necessary. Suppose light, and now light is there from there, and no air is there, no atmospheric gases is there. Is it possible to receive light? No. No or yes? Yes. Light can travel without any medium. That we are going to discuss now. Okay. Some type of wave require medium for propagation. Some type of wave does not require medium for propagation. Okay. That is, according to what they move through, that is medium, two types of waves are there. One is electromagnetic wave or mechanical wave and mechanical wave. Electromagnetic wave is also called as non-mechanical wave. We have studied some of the electromagnetic waves. What is the electromagnetic wave? Come on, say. We studied electromagnetic waves in electromagnetic wave topic itself. I think you can say in order as increasing wavelength or decreasing wavelength, or increasing frequency or decreasing frequency. That's your wish. But say some electromagnetic wave. Starts from gamma rays, X-rays, then gamma rays, X-rays, UV, ultraviolet rays, visible light, IR infrared rays, and then microwaves, radio waves. How many waves are there? 7 electromagnetic waves. For all the electromagnetic waves does not require material medium for propagation. That's why we are calling non-mechanical wave. Mechanical wave requires medium for propagation. Now down, mechanical wave requires material medium for propagation. And electromagnetic wave, not mechanical wave, does not require medium. Medium is not necessary. Okay. Sound wave is a mechanical wave. That's why it requires material medium. Suppose no air in the space, then you can't hear my voice. But light is an electromagnetic wave. So if there is a free space or vacuum, but you can receive the light energy. So what are electromagnetic waves or non-mechanical wave? Is a wave which does not require material medium for propagation. And mechanical wave require medium or material medium for propagation. That is mechanical wave. And see, this one we discussed already. Waves that can travel through matter or empty space where matter is not present. Matter means medium. Medium is not necessary. No material medium is necessary. That is a electromagnetic wave or non-mechanical wave. This we studied gamma ray, X-ray, UV light, visible light, IR. In IR what they mentioned? Yes? In IR what object is mentioned here? Thermometer. What does that represent? Already we said infrared radiation is having peculiar property, that is the heating property, heating sensitive, and microwave radio waves. And mechanical waves classify into two. Okay, mechanical wave classify into two. Actually here mentioned, these are all comes under mechanical wave: water waves, earthquake or seismic waves, sound waves, waves that travel down or rope or spring. These are all comes under mechanical wave. These waves are all require material medium for propagation. Okay, and basically mechanical wave is classified into two. One is transverse wave and another one is longitudinal wave. Longitudinal wave. Transverse wave and longitudinal wave. Okay. Transverse wave, longitudinal waves. Transverse waves. The particles of the medium vibrate perpendicular to the direction of propagation of wave. That is called transverse wave. Best example, waves produced on the surface of water, that is the ripples. Okay, in there, suppose there is a ripples are forming like this, and ripples will start to move from this drop point to this side. And if you drop any leaves there, what will happen means leaves will float up and down and waves will coming like this. It means particles not transferring, it's just by vibration it will transfer energy only. And the particle vibrates perpendicular to the direction of propagation of wave, that is called transverse wave. Okay, direction of propagation of wave is this direction. Particles vibrate in this direction, y-axis. This is x-axis. Okay, that is if the particles of the medium vibrates perpendicular to the direction of propagation of wave, that is called transverse wave. And transverse wave produces two things: crest and trough. First definition, note down. What is transverse wave? The particles vibrate perpendicular to the direction of propagation of wave, that is called transverse wave. And transverse wave produce two things: crest and another one trough. What are crests? Crest is the maximum displacement along positive direction, that is called crest. Crest is the maximum displacement along positive direction. This is crest. Trough is the maximum displacement along negative direction, that is trough. Okay, what is trough? Trough is the maximum displacement along negative direction. And distance between two crest or trough, that only wavelength. Distance between two successive crests or two successive trough, that is only wavelength lambda. Okay. See, crest I said. What is crest? Maximum displacement along positive direction. Trough, maximum displacement along negative direction. And this maximum displacement is also called as amplitude. Distance between two successive crests is wavelength. Okay. Longitudinal waves. If the particles of the medium vibrates parallel to the direction of propagation of wave, are called longitudinal waves. What are longitudinal waves? The particles of the medium vibrate parallel to the direction of propagation of wave, are called longitudinal waves. Sound wave is a transverse waves or longitudinal waves. Sound wave is a transverse waves or longitudinal wave. Example for longitudinal wave is sound wave only. And example for transverse wave is waves produced on the surface of water, vibration of a string instrument. That and all example for transverse wave. And vibration in spring is longitudinal wave. Sound also transfer as spring waves only. And just like in Transverse wave I produce crest and trough. Like that in longitudinal wave, compression and rarefactions are formed. Compression means region having high pressure or high density. Compression is the region having high pressure or high density, and rarefaction means region having low pressure or low density. Rarefaction means region having low pressure or low density. That is rarefaction. Okay. Noted? See, I said no, spring wave is a best example for longitudinal wave, and here is a region having high density. So this is compression, and here is a region having low density, rarefaction, and this is compression, this is rarefaction, and distance between two successive compression or rarefaction, that is equal to lambda wavelength. Just like distance between two successive crest and trough in longitudinal wave, distance between two successive compression and rarefaction is called wavelength lambda. And here, which is a transverse wave, which is a longitudinal wave? First longitudinal wave, and this is a transverse wave. Vibrate perpendicular. And here, this is how spring waves produced, moving like this. Okay, compression, rarefaction, like that, it will transfer distance between, and this will be a transverse wave. As per this is a transverse wave, and this is the longitudinal wave. This is compression, crest and trough. This is transverse. And compression, that's crest, trough. Distance between two trough is wavelength. And here, what's the name of this? This is rarefaction. This is compression. Rarefaction, compression, rarefaction. Distance between two rarefaction or two compression, that is only wavelength. Okay. So this is a wave, transverse and longitudinal wave using a spring. Okay. Next, speed of longitudinal waves. V equal to square root of E by rho. V equal to square root of E by rho. E is the modulus of elasticity. What is modulus of elasticity? It is the elastic constant. Rho is the density of the medium. Rho is the density of the medium. And speed of longitudinal wave in a solid in the form of rod is given as V equal to square root of Y by rho. Here we said E is a modulus of elasticity. We didn't mention whether it is a Young's modulus or rigidity modulus or bulk modulus. Just Young's one modulus constant. Now here Y is the Young's modulus of the solid rod, and rho is the density of a solid. And speed of longitudinal wave in fluid is given by V equal to square root of B by rho or K by rho, because we used K by rho only in our theory. Here K or B is only a bulk modulus. We studied K, that's why I have given K. But in many places, bulk modulus is given in B repeatedly, and Young's modulus is used in Y or Q. Q also will be given for Young's modulus. Same way, bulk modulus K or B. Okay. Then speed of longitudinal wave in fluid, either in liquid or gas, equal to V equal to square root of K by rho. That is, K or B is the bulk modulus and rho is the density of the fluid. Noted? Newton's formula. Newton assumed that propagation of sound wave in gas is isothermal process. What is isothermal? Iso means same, thermal means temperature. Temperature maintained constant. That is isothermal. Okay. So according to Newton, actually Newton tried to found the velocity of the sound waves. Velocity of the sound waves. That is V equal to square root of P by rho. Here P is a pressure of the gas and rho is the density of gas. But he found the answer as 280 meter per second. But what is the velocity of sound? Velocity of sound V equal to 3 into 10 power 8 meter per second, that is velocity of light. I asked velocity of sound. 330 meter per second. This is the velocity of sound. This is 330 meter per second also at 0 degrees Celsius only. Okay. But Einstein found this answer as 280 meter per second. So this is one of the failure for Newton's formula. What is the failure means? He used that gas, that is a sound waves which propagate through gas is the isothermal process. Temperature maintained constant, he said. But that is a wrong concept. So that is corrected by next person, that is called Laplace. That is called Laplace correction. Okay. So V equal to square root of P by rho. He modified slightly, is not root of P by rho, something added. Then only we will get 330 meter per second. As per Newton, 280 meter per second only we got. Laplace correction, also called Laplace formula. That is V equal to gamma P by rho. Gamma we studied now previously, gamma equal to Cp by Cv, and that is for gamma for R 1.4 we studied now, that one. Gamma equal to 1.4. And Laplace assumed that sound wave propagation is an adiabatic process. What is adiabatic process? There will be a change in temperature, but no heat enters or leaves the system. There may be a change in pressure, change in volume, change in temperature also, but no heat exchange or leaves the system. That is the adiabatic process. And by applying adiabatic process, V equal to gamma P by rho, and gamma is a constant, Cp by Cv 1.4. Then by applying this, he was able to get the answer as 331.3 meter per second. This is agrees with the experimental value. Okay. Noted, no? Next. I went reverse. Effect of pressure. For a fixed temperature, when the pressure varies correspondingly, density also varies, such that ratio P by rho becomes constant. For a fixed temperature, when the pressure varies correspondingly, density also varies such that P by rho maintain constant. This means that the speed of sound is independent of pressure. That is what we are going to discuss is velocity of sound in air. When pressure changes, what is the velocity? And when temperature changes, what is the velocity? Like that we will discuss. Effect of pressure, effect of humidity, effect of temperature, like that. First is effect of pressure. That is a various factor affects the velocity of sound. Now, pressure. When pressure increases, density also increases, then P by rho maintain constant. Therefore, speed of sound will not change. Speed of sound also, no effect, no change. But in practice, temperature is not same at top and bottom of mountain, so there will be vary. But generally, on the earth surface, there is no effect of pressure. Note down, effect of pressure has no effect. So, velocity of sound is independent of pressure. How is possible? When pressure increases, density also increases. So, P by rho maintain constant. So, no effect of pressure on velocity of the sound in a air medium. Effect of temperature. V is proportional to square root of T. And V naught be the speed of sound at temperature 0 degrees Celsius. V naught is the temperature at 0 degrees Celsius. Then formula is V equal to V is proportional to root T. This under some steps. Directly you can write this formula. V equal to 331 plus 0.60 T meter per second. V naught is 331 meter per second. That is velocity of sound at 0 degrees Celsius. 331 plus 0.60 into T. T is the temperature in degrees Celsius. Suppose you want to find temperature at 10 degrees Celsius. So velocity of sound at 10 degrees Celsius. Then you can do V equal to 331 plus 0.6 into 10 equal to 331 plus 0.6 into 10. How much? 0.6 into 10. 0.6 into 10. 6. Is it so? 6.06. Then 331 plus 6. 337 meter per second. So, velocity of a sound at air at 0 degrees Celsius 331. When temperature increases, what about the velocity? Increases or decreases? Increases. So, speed of sound in air increases by 0.61 times of the T. Okay. Note that when the temperature is increased, the molecules will vibrate faster due to gaining thermal energy, and hence speed of sound increases. That is the actual concept inside. Okay. Noted? Effect of density. Consider two gases with different densities having same temperature and pressure. Then speed of sound in two gases V1 equal to gamma 1 P by rho 1 and V2 equal to gamma 2 P by rho 2. And here we are assuming temperature and mesh pressure are constant. Same temperature and same pressure. Then V1 equal to square root of gamma 1 P by rho 1, V2 square root of gamma 2 P by rho 2. Then V1 by V2 equal to square root of rho 2 by rho 1. So, from this what is the relationship? V1 is inversely proportional to rho 1 or simply V is proportional to rho. So, when density increases, what about speed? Inversely proportional. When density increases, what about speed? Increase or decrease? Decrease. V is inversely proportional to density. Okay. Effect of moisture or humidity. We know the density of moisture is 0.625 of that of dry air, which means presence of moisture in air or increase in humidity decreases its density. Therefore, speed of sound increases. As density decreases, speed of sound increases in humid air. During rainy season, that's why you may observe our voice as a very clear voice. Suppose voice is not clear means during rainy season, throat may be infected. And if throat is not infected, then voice will be clear because of decrease in density. So, due to decrease in density, speed will be increased. Effect of wind. Speed of sound is also affected by blowing of wind. In the direction along the wind blowing, speed of sound increases, whereas in the direction opposite to wind blowing, speed of sound decreases. Okay. So, along the direction of wind, if you speak means, then sound speed will be increasing. Opposite side decreasing. Okay. Effect of temperature on velocity, V2 by V1 equal to square root of D1 by D2 in terms of beta as cubical expansion. That is a volume expansion we are doing. So based on that, V2 by V1 equal to square root of T2 by T1. We studied, no, that is coefficient of linear expansion and coefficient of areal expansion, volume expansion. Based on that, if you do, V2 by V1 equal to square root of T2 by T1. From this, V2 is proportional to root of T2, or V is proportional to T. V is proportional to square root of T. Noted? Wave traveling in opposite direction. When two waves of same amplitude and frequency traveling in opposite direction, y1 equal to a sin kx minus omega t and y2 equal to a sin kx plus omega t. Then y equal to y1 plus y2, that is equal to 2a sin kx cos omega t. This is the two waves of same amplitude or frequency traveling in opposite direction. And opposite direction in the sense, this is moving in forward direction and this will be in backward direction. Okay, this is for forward direction, positive direction. You can say not forward, positive direction. According to this formula, this wave traveling in what direction? What axis? Positive x-axis. And this will be negative x-axis. Okay. Positive x-axis, negative x-axis. Equation of stationary wave. Y1 equal to a sin 2 pi into t by t minus x by lambda. Actually, this is derived from this only, kx minus omega t. From this only, we are simplifying for t by t minus x by lambda. This is incident wave. And y1 equal to plus or minus a sin 2 pi into t by t plus x by lambda. This is for reflected wave. And for stationary wave, y equal to y1 plus y2. That is equal to plus or minus 2a cos 2 pi x by lambda into sin 2 pi t by lambda, t by t. Here lambda is a wavelength, t is the time period, x is the position, small t is the time, a is the amplitude. For positive sign, antinodes are at x equal to 0, lambda by 2, lambda, 3 lambda by 2, etc. And nodes at x equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, etc. That is, suppose the waves are formed like this, then we can say this point is node and this is antinode. Node, antinode, node. So antinodes are formed at x equal to 0, lambda by 2, lambda, 3 lambda, like that. And nodes are formed at lambda by 4, 3 lambda by 4, 5 lambda by 4. For negative sign, x equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, and nodes at x equal to lambda by 2, lambda, 3 lambda by 2. And distance between two successive nodes or antinodes is lambda by 2. And distance between one node and antinode is lambda by 4. Okay. Distance between two successive nodes or antinodes is lambda by 2, and distance between one node and next antinode is lambda by 4. Nodes point of zero displacement. That's why I said in this region, I said zero displacement. This is node and this is antinode and this is node. Antinodes are point of maximum displacement. So antinodes at maximum displacement, zero displacement is nodes. Noted? nodes amplitude equal to 0, then 2a sin kx equal to 0. How we are getting that one? X equal to 0, pi by k like that. Therefore, x equal to 0, lambda by 2, lambda by 4 like that. For antinodes, x equal to lambda by 4, 3 lambda by 4, 5 lambda by 4. Lot of waves are there means its position. X is the position of the nodes and antinodes. And nodes are completed at rest. This I said, nodes, antinodes, and distance between. This is a one complete wave for that. Then this is a stationary wave. Distance between one node and one antinode. One node and one node is lambda by 2. One node and one antinode is lambda by 4. That and all we discussed. And nodes and antinodes are alternatively placed. Nodes, antinodes, nodes, antinodes, nodes. Alternate next to next. This is the other way of stationary waves. And vibration in a stretched string fixed at both ends. Transverse standing waves with nodes at both ends of the string are formed. L equal to n lambda by 2, and the frequency of oscillation is nu equal to v by lambda or nv by 2L. And its mode of vibration nu equal to p by 2L into root of t by m. Here T is a tension, m is a mass per unit length of the string. Nu is a frequency, v is a velocity, and p equal to 1, 2, 3. Note down this formula. Nu equal to p by 2L into root of t by m, and p is a pitch of the note. P is a pitch of the note, and this value is, if it is 1, it is a fundamental. Fundamental frequency. Okay, fundamental or first harmonics, we will say, or first harmonics. And P equal to 2. That is second harmonic or first overtone. Overtones. Or first overtones. Okay. And law of length. Nu is inversely proportional to L, or nu into L equal to constant. This is the law of length. And this is fundamental frequency, x or p or n equal to 1, nu naught equal to v by 2L, and for second harmonic of first overtone, the n equal to 2, 2v by 2L, like that, nth multiple value. And is fixed at 1n. Frequency of oscillation is nu equal to v by lambda, that is equal to n minus 1 v by 4L, and for fundamental frequency n equal to 1 means v by 4L. It is also called first harmonic. First overtone 3v by 4L, like that. Only odd harmonics are present. Odd harmonics means 1 is to 3 is to 5, like that it goes. That is odd harmonics are present. And organ pipe, in an organ pipe closed at one end and odd harmonics only present, as one time 1 is to 3 is to 5 I said. And in an open organ pipe at both ends, both odd harmonics and even harmonics are present. Here 1 is to 2 is to 3. Its frequency range is. Okay, is 1 is to 3 is to 5, 1 is to 2 is to 3. And this is the closed organ pipe, which is closed at one end. This is the open organ pipe, opened at both the ends. Okay. This is odd harmonics only, 1 is to 3 is to 5. This is 1 is to 2 is to 3. All harmonics are present. And note down this formula. V equal to 2 nu into L2 minus L1. L2 minus L1. So, one minute. L2 minus L1. End correction formula E equal to L2 minus L1 by L2, where we are using is resonance column apparatus. We are using in resonance column apparatus. This is one lab to determine the tuning fork frequency. Column apparatus. Resonance. When one object vibrates another without touching, the two objects resonate at the same frequency and amplitude increases. Already I said for resonance condition, amplitude will be increases. So amplitude increases means sound will be increases. That is, for example, two tuning fork. This is a tuning fork. I don't know whether you have seen or not. For showing I am mentioning. Two tuning fork. Both will vibrate with same frequency. Then apart from that sound, it vibrates with extra sound. That is the amplitude. Amplitude increases. Okay. Same only in instrumental or music instrumental. Suddenly some sound will be appear. That is when it will, sudden noise will be there. Why it's happened means that is due to resonance only. The frequency of one instrument and other instrument will be matched. Then resonance condition will occur. It starts to vibrate with maximum amplitude. That way some string sound you may observe suddenly. We may feel that is a noise. That is due to resonance. And this I said, this is for open organ pipe and closed organ pipe. This we discussed there itself. And waves having different frequencies. Beats are formed by the superposition of two waves of slightly different frequencies moving in the same direction. The resultant effect heard in this case at any fixed position will consist of alternate loud and weak sounds. Beats frequency is number of beats per second equal to difference in frequency of two sources. Suppose two sound sources are vibrate with nearly equal frequency, then beats are formed. Beats means increasing intensity and decreasing intensity slowly. Then nu2 equal to nu1 plus or minus b. And if prong of the tuning fork is filled with wax like that, its frequency increases. If prong of the tuning fork is loaded with little wax, its frequency decreases. Then these facts can be observed by positive and negative sign. Based on this, what is the use of beats means? By knowing one frequency and we can determine the frequency of another tuning fork. Okay. Doppler effect, this will be a last topic. What is Doppler effect? Doppler effect is the apparent change in the pitch or frequency, when there is a relative motion between the source and the observer. When there is a relative motion between the source and observer. This is Doppler effect. What is Doppler effect? Is the apparent change in the pitch or frequency when there is a relative motion between the source and the observer. That is called Doppler effect. I'll say one example. Suppose you are standing in this station, railway station, not police station, railway station. And train is coming with sound, whistling sound. You have closed your eyes. When train is coming towards you, how is the sound frequency? Increases or decreases? When it is coming towards, it will increases. Same way, when it is moving away from you, frequency decreases. But actually, is there any change in frequency of whistling of sound? No. It's appearance only. For us only it will be increases when it is moving towards us and decreases when it is receding away from us. This is Doppler effect. What is Doppler effect? Apparent change in the pitch or frequency when there is a relative motion between the source and the observer. That is called Doppler effect. These things only we are observing, and we are doing this in astronomy also. Suppose frequency of light is decreasing, then that particular star is moving away from us. Suppose frequency of the light is, that is as light is increasing, then that star is moving towards us. Same thing, same Doppler effect is applied in astronomy also. Write down the formula, that is V is the velocity of sound. VO is the velocity of the observer, that is you are standing in the station. Vs is the velocity of the source, that is a train is moving. And suppose you are standing in station means VO is at rest. VO equal to 0. Suppose train is whistling sound and start to move and it is at rest in a station. You are running, then VO is in motion having some velocity. Okay. And train is also moving and you are also running and trying to chase the train and get into the train. That is a danger, that both are in motion. And general formula, nu dash equal to V plus Vm minus Vo by V plus Vm minus Vs into Vo. And Vm is the medium, we will assume Vm will be rest. Okay, Vm will be rest. And general formula I will give first, that is instead of this, nu dash equal to V minus Vo by V minus Vs. Suppose Vs is at rest and you are moving towards the train, then frequency will be increase or decrease. That is Vs, source is at rest, train is at rest and making a siren sound, and you are moving, running towards the train. How is the frequency? Increases or decreases? Increases. That is nu dash equal to V plus Vo by Vs is at rest, so by V. Here what is V? V is the velocity of the sound into nu. Nu is the actual frequency of the sound. Okay. And nu dash equal to, you are moving away and source is at rest. Then what is the formula? Source is at rest, you are moving away from the train, running away from the train. Then frequency will be decreases, no? Then V minus Vo. You write down another formula. This is moving away. Okay. Understand? So now source is at rest and observer is in motion. First one is moving towards the source. Second one moving away from the source. Both the formula we discussed. Then, now observer is at rest. We are at rest. And so in top Vo will be 0. And source is moving towards you. Frequency is increasing or decreasing? Increasing. So V minus Vs. Okay, into frequency nu. Now don't, this is for source moving towards you. Source is moving away from you, decreasing, so plus. Write down another formula, plus. Okay. Now you understand the concept, no? And Vm also is there. Vm will be velocity of the medium. We are assuming this will be rest only.